So today we'll be looking at partial derivatives of functions. Now, up to this point, you are familiar with the idea of a derivative, right? You are familiar with this definition of a derivative. Let's say if f of x, if you have a function f of x, right? So this is a function, then f prime of x is equal to limit as h goes to 0 f of x plus h minus f of x divided by h. This is the definition of a derivative of a function of one variable, okay, of a single variable. Now, I mean, as in real life, in economics, in physics, in engineering, we have functions of many variables, and what we need to do is we need to find the derivatives of those functions with respect to particular variables. For example, you have a temperature function, right? Temperature function that is a let's say temperature is a function of the temperature in a room is a function of the okay, let's simplify this. Is a function of position, which is x, which is given by x, and time t. So let's say you want to find t for temperature, x for position, the vec t for temperature, x is the position. Let's say we live in a one-dimensional world, so we need only one variable to specify the position, and small t is for time. Right? So let's say you want to find the rate at which the temperature varies with respect to time at a particular point in time, t0. Let's say you want the answer to I want the answer to answer to the following question. What is the rate of change of temperature at x equals x0 when t is equal to t0. Now, well, you could try using okay, so first of all, how would you find this? Well, one way of doing it would be to with this, basically, to find this limit, to find out the value of this, right? x0. You let t0, you let t vary, right? That's t x0 t0 divided by h, right? And you want to make this variation in t as small as possible, right? So remember, x0 is constant, it stays constant, but t0 is vary. And so if you want to make h as small as possible, you take the limit as h goes to 0. In fact, to be more instructive, what we should do is we should, instead of using h, we should use delta t, right? Delta t, limit as delta t goes to 0, t0 plus delta t divided by delta t. Right, so this is like taking the derivative. What we're essentially doing here is we're taking the derivative. We are taking the derivative with respect to t while keeping x constant, right? X is a constant. I mean, x is a variable, right? But we're taking it to be constant. We're assuming that it's constant, and we're taking the derivative with respect to t. With respect to, I mean, small t, with respect to time. So this is how. So this motivates for us the definition of a partial derivative. So how do we define a partial derivative? It's very similar to how we define a total derivative. We say that the partial, this is how we put it. The partial derivative. Okay, first of all, you start with given f of xy is specified on some domain as a function on some domain, the partial derivative of f with respect to x is denoted by partial f over partial x, right? So we pronounce this partial f over partial x, and this d is known as a curly d, right? So this is a curly d. Okay, so df over d. I mean, if you said df over dx, people would confuse it with the total derivative, right? So it's a partial f over partial x, and if you want to find the partial derivative at a particular point, you say partial f. I mean, over partial x at the point x naught y naught on its domain, right? So this is the partial derivative at the point x naught y naught on its domain, and this is defined to be equal to limit as h goes to 0 f of x plus h minus f of x naught plus h. Remember, this is a function of two variables, minus f of x naught y naught divided by h. Now similarly, partial f over partial x partial y at x naught y naught is defined to be equal to the limit as h goes to 0 f of x naught y naught plus h minus f of x naught y naught divided by h. Alright, so the partial derivative then is just like the total derivative, except that you take the other variables to be constants. right? So there's a I mean there's a plethora of notation here. So for example, you can write what you can do is you can write partial f over partial x in the following ways. Right, you can write this is okay. So this is the first way you can write it. You could write as f subscript x, and instead of f prime, you have f subscript x. You can have f subscript x of xy, right? You can have f1, because remember x corresponds to 1 and y corresponds to 2. You can write d1f, you can write dxf, and so on and so forth. This you can partial f or partial y can be written as fy, xy, f sub y, f2, this is equal to d2f, or capital dyf. Alright, cool. So there's another way of doing it. I mean, if z equals f of xy, you can write df over partial y over partial x as partial z over partial x. Alright, so so let's try find it. Let's look at a few examples, right? If you have, for example, okay, so we'll start with functions of two variables, because that helps us give it a geometric interpretation, and then hopefully work upwards. Right. So so let's say we have a function f of x y that is equal to x cubed plus x squared y cubed minus 2y squared, right? And we want fx at 2, 1, and we want fy at 2, 1. Now, to find f sub x, right? To find f sub x, you need to hold y constant. To find f sub x, you need to hold y constant. So, and differentiate with respect to x. So f sub x, xy, equals thrice x squared plus twice xy cubed. And of course, f sub x at 2, 1 is going to give me okay, this is 4, 12. Let's just plug this in, right? 2, 1 is a point in its domain. Right? So 3, 2 square plus 2, 2, 1 cubed, which is equal to 16. Right? So this is equal to 16, and when you're finding f sub y, you hold x constant, right? So this is, so here you're holding y constant, hold y constant, and here you're holding x constant, x, y, hold x constant. So f sub y equals so if you hold x constant, the first term goes to 0. The second term becomes 3y square x square. This goes minus 4y. Right. So f sub y at 2, 1 is then equal to 3, 2 square, 1 square, minus 4 times 2, 12 minus sorry, 4 times 1, not 2, 4 times 1. So it's 12 minus 4, which is equal to 8. Right, so so let's look at a more complicated example. We have f of xy equals sine x over 1 plus y, sine x over 1 plus y. We need to use the chain rule here. So let's say we want to find df over dx and df over dy at xy. Okay, so df over dx at xy equals, okay, so first you differentiate the whole thing, cosine, cosine, should have used a bigger bracket, cosine x over 1 plus y times d over dx of x over 1 plus y, right? So this is a function of x and y. This is a composite function, so we use the chain rule. So this becomes 1 over 1 plus y cosine x over 1 plus y, right? And df over dy, I mean, here what we're doing here is we're using the chain rule for functions of one variable. Later on we'll use the chain rule. There's a separate chain rule for functions of multiple variables. We'll look at that later. df over dy xy equals, again, differentiate the sign, cosine x over 1 plus y, then differentiate what's inside the sign, 1 plus y, so this becomes x cosine x over 1 plus y, right? And this, for this you get this y negative 2, right? So yeah, so you have negative x over 1 plus y squared cosine x over 1 plus y. Right, so that's df over dy. So we're using the chain rule for total derivatives. This is the chain rule. The chain rule that we're using here is a chain rule for total derivatives. Soon we'll use a different chain rule. That's a chain rule for partial derivatives. And the chain rule, okay, so for partial derivatives, the chain rule usually occurs when in a situation where f is a function of xy, right? F is a function of xy, and x and y are themselves functions of other things, right? Let's say u and v. So let's say if you want to find df over du, how would you find it from this? So that's how you would use the chain rule for partial derivatives, right? That's where you would use the chain rule for partial derivatives, but that's not required here. Okay, so now let's try to, now since we're working in 2 and 3 dimensions, what we'll try to do is we'll try to assign a geometrical interpretation to partial derivatives, right? Okay, so let's try to assign a geometrical interpretation to partial derivatives of functions of two variables, right? So if you recall, for functions of one variable, if you had y equals fx, right? You had and you sketched it, you would get a curve in R2. So you have this and this, these axes, and if you sketched it, sketch, and you get a curve, right? So this is y x fx, right? And you want to find, so you're given a point x naught y naught, right? This is x naught y naught, and actually I should write this as x naught f of x naught, right? So this point is going to be x naught f of x naught. Now what does this signify? What is this equal to? The x equals x naught. Well, this tells you the gradient of the tangent line at x naught, comma, f of x naught. Right, so you draw a tangent here. Call this line L. So df over dx gives you the gradient of L, right? I.e. gradient of L. Cool. So now you have a function of two variables, right? You have z equals f of x naught, f of x and y. I want to find the interpretation of partial z over partial x at x naught y naught and partial z over partial y at x naught y naught. How do we interpret this? Well, draw your axes, then you sketch your surface, right? Sorry about that. Let's label our axes. And we sketch our surface. Right, so this surface given here, this surface is z equals f of x, y. Now we want to find, so we want to find out what dz over dx and dz over dy, what they mean. Okay, so when you restrict, okay, so when you're finding dz over dx at x naught y naught, right? When you're figuring this out, right? dz over dx at x naught y naught, right? So you're taking y to be constant, right? Take y to be what you're doing is taking y equals y naught to be a constant, right? So what does that mean? You're essentially so when you take y is equal to y naught to be a constant, right? So you're essentially finding the intersection. You're essentially finding the intersection of a curve of the plane y is equal to y naught with the surface, right? So when you do that, when you set y is equal to y naught in f of xy, you are essentially finding the intersection of the surface z equals f of xy with with the plane, with the plane y equals y naught, right? So this intersection gives you a curve. This intersection . gives you a curve on the surface. Right, so let's say this point is this point is y is equal to y naught. This point is x naught. Sorry about that. Right choice of color. Let's go with red. X naught, y naught. Right. So this point is my x naught, y naught. Right. So when we restrict y equals y naught, right? So I set y is equal to y naught. What I do is I get a curve that passes through here. Right, so that's what I'm getting, a curve. And on this curve, on the red curve, y is equal to y naught. On the red curve, y equals y naught. Now, what is dz? What is varying? Right? X is varying, right? Y is taken to be constant, equal to y naught. But x is varying, so dz over dx gives you the gradient of the tangent to this curve, right? And what do I mean by gradient? By gradient we mean gradient is how z varies when you vary x or y. So what we're essentially doing is we're essentially finding the gradient of the tangent at x naught y naught as x is varying, right? So so let's call it tangent t1. Let's call this tangent t1. This tangent, let's call it. So let's see, you have a tangent here. So let's just do the tangent. Let's call it t1. I'm running out of colors. t1. Right, sorry. Again, poor choice of color. So undo that. And let's choose. We'll go back to green. Let's call this tangent t1. Right now, and when you set okay, so this is the tangent that you get, whose gradient you get when you find dz over dx. Now, when you vary, when you find it, now when you're evaluating dz over partial z over partial y, well, you're taking x to be constant and you're varying y. Now when you take x to be constant, again, you get a curve. When you take x to be constant, you get another curve that is the intersection of x equals x naught and f of xy. So when you vary x, you get the intersection of a curve of the plane x equals x naught and the surface z equals f of xy. So let's say this is that curve, right? And of course those curves, both curves, and they intersect at x naught y naught. So let's say this is that curve, and when you find dz over dy, you get a tangent that is whose gradient is given by dz over dy, partial z over partial y, sorry. Right, so this is the second tangent, tangent 2. Okay, so this diagram is getting a little messy, so here's what we'll do. We'll refer back to our book, the diagram given in the book. Alright, see that? So t1 and t2, so the partial derivatives uh, thus the partial derivatives fxav and fyav can be interpreted geometrically as the slopes of the tangent lines at p ABC, meaning okay, so they have three coordinates, of course. So those three coordinates are basically your P, A, B, and F of AB. Right. So to the traces C1 and C2 of the planes y equals B and x equals A. So instead of x naught, y naught, they used AV. So basically, what they're doing here is that they're setting the curve C1 equal to the intersection of the plane x equals A and the surface, and the curve C2 is the intersection of the plane y equals B to the with the surface. And the partial derivatives, they give us the tangents, the slopes of the tangents at these points, right? So so the tangent to C1 is T1 and the tangent to C2 is T2. Okay, so so for example, if we have a surface which is, this is my z of xy, 4 minus x squared minus 2y squared. So I want to find fx11 and fy11, right? So the partial derivative of x with respect to f with respect to x at 1 1, and the partial derivative of f with respect to y at 1 1. Right. So first thing we do is find fx xy, which f sub x xy, which is basically you setting y to be constant and taking the derivative with respect to x. So the first term becomes 0. So 4 is, obviously constant. X is negative x squared becomes negative twice x, and negative 2y squared becomes 0. And then you set x equals 1, y equals 1, and you get minus 2. And f sub y, is negative 4y. So you set set this equal, the point equal to 1, 1, and you get negative 4. Right. So what do these derivatives mean? Okay. So first of all, what we need to do is we need to find the intersection of the surface with the planes x equals 1 and y equals 1. So this is this graph here, right? This is a paraboloid. Now, what's important is that the intersection of the plane x equals 1 with the paraboloid gives you the curve C1, right? This is the plane and this is the paraboloid, and their intersection gives you the curve C1. This is the plane x equals 1, I'm sorry, x equals 1, yeah. X equals 1, and that gives you the curve C1, and the intersection of the plane with the curve C2, intersection of the plane y equals 1 with the paraboloid gives you the curve C2. Now, what does partial f over partial x and partial f over partial y, what do these give you? Right, at 1, in fact, the standard notation is to write this and then 1 is a subscript, right? You write, let's write 1 is a subscript. Right, so what do these give you? So this gives you partial f over partial x gives you partial f over partial y gives you the slope of the tangent to the curve C1, right? Remember here, y is what's varying, right? So partial f over partial y gives the slope of this tangent, and partial f over partial x gives you the slope of this tangent at 1, 1, 1. Okay, great. So we define the body mass index of a person as And of course, they can be interpreted, partial derivatives can be interpreted as rates of change. Okay, now what happens if, let's say, z itself is a function, z is a function of x and y, but we don't know z explicitly, right? We know z implicitly, but we don't know z explicitly. So for example, so what the situation I'm talking about here is z equals f of xy, right? But it's very hard to find z. It's very hard to make z the subject of the formula, to separate z out. So how would we deal with the situation? Well, what we can so one example of this would be example 5, right? So in that example, you have x cubed plus y cubed plus z cubed, right? So you have x cubed plus y cubed plus z cubed plus 6xyz plus 4 equals 0. Now it's going to be extremely difficult for you to isolate z in this formula, right? It's extremely difficult to isolate z in this, to put z on the left hand side. So so the best you can do is use implicit differentiation, right? So I want to find dz over dx. How would I find that out? Right? We differentiate implicitly with respect to x. Right? So in that case, y is a constant and z is a function of x only, since y is a constant. Okay, so differentiate this with respect to x, you get 3x squared. Differentiate this with respect to x, you get 0. Differentiate this with respect to x, by the chain rule you get 3z squared dz over dx. And differentiate this with respect to x, you get 6y, and then you differentiate the product of xz with respect to x, so you get x dz over dx plus z. Right? So and you differentiate 4 with respect to x, you get 0. And of course on the right hand side you have 0. So that tells you that okay, let's isolate dz over dx. So dz over dx is then equal to negative x squared plus 2yz. I mean, if you divide everything by 3 and then you take to the left hand side, and of course downstairs you have z squared plus 2xy, right? Similarly, when you find dz over dy, you treat x to be a constant and z to be a function of y only, right? And that's how you could find dz over, so when dz, so this becomes 0, right? The x cubed becomes 0, y cubed becomes 3 y squared plus, and this becomes 3z squared dz curly d. Actually by d I mean curly d. I know I told you not to use I know I told you not to say dz over d dx or dz over dy to when you're talking about partial derivatives, but this is a force of habit. I mean it's convention, but you should say what you should say, partial z over partial y, right? Plus 6x times, of course, y dz over dy plus z equals 0. So then you get dz over dy equals negative y squared plus 2xz, right? And downstairs you have z squared plus 2xy. y. Right, so that is dz over dy. Okay, so great. So we've looked at implicit differentiation. How about now? What if I gave you functions of now? So far we've been dealing with functions of two variables only. What if I give you functions of 3 variables, 4 variables, any number of variables? Well, the definition can be extended, right? The definition of a partial derivative for functions of any number of variables can be extended. That's, for example, you want to find so you have f of x, y, z, right? And you want to find this. Well, this is actually defined as the limit as h goes to 0, f of x plus h, comma y, comma z, minus f of x, y, z divided by h, right? Or if you want to talk about so if you have a function that has more than 3 variables, let's say xi, let's say it has n variables, and you want to find the derivative with respect to xi. Well, this is equal to the limit as h goes to 0, f of x1, x2, xi plus h, xn minus f of x1, x2, xn divided by h. So it's pretty easy to extend the definition to. It's very intuitive. It's very trivial to extend the definition to functions of more than 2 variables. All right. So so df over dxi. This is something we would call d sub I f. All right. Now of course we could have higher derivatives, right? We could have higher derivatives of higher partial derivatives of f, right? And they may not all be with respect to the same variable. So for example, you could have f of f xy, right? Okay, so fxx, for example, let's start with fxx. This is basically equal to d square f over dx square. Are you familiar with this? Partial square f over partial x square. fxy is equal to partial square f over partial x partial y. Right? So no, actually this is equal to partial y partial x. It's the reverse, right? Partial y partial x. Partial y partial x. So what are you doing here? You are differentiating with respect to x first, right? Differentiate with respect to x first, then with respect to y. So this is actually f x y, right? Now for what is fyx? For example, fyx this is actually here you're differentiating this. Here what you're doing is you're differentiating with respect to y first and then with respect to x, right? Differentiate with respect to y first, differentiate then with respect to x, right? So so these are called mixed partial derivatives, right? Now, so for example, if you have f of xy equal to thrice x cubed plus x squared y cubed, x cubed plus x squared y cubed minus 2y squared, well, then f of x, fx, right, equals f sub x 3x squared plus 2xy cubed, right, and fxy equals 6xy squared, right? You differentiate with respect to x first and then with respect to y, and the fxx is equal to 6x plus 2y cubed, and then you have fy equals fy is equal to 3x squared y squared minus 4y. Fyx is equal to of course you differentiate with respect to x first, then 6xy squared, and fyy equals so this equals 6x squared y minus 4, right? Now notice something here. fxy is equal to fyx. That is not a coincidence, right? fxy equals fyx is not a coincidence, right? This is a case of a theorem that is known as Clairaut's theorem, right? Clairaut's theorem, which is, I'm going to include the proof later on, but I'm just going to state the theorem now. Clairaut's theorem. So what's important is that you understand what the theorem is saying. Right, so this is Clairaut's theorem, and what it says is Clairaut's theorem. What it basically says is that if f is defined on a disk D that contains the point AB, so you have a so f is defined on a circle. F is defined on a circle. Let's call this circle D. And on that circle you have the point AB. So the domain of f includes this circle D. And this circle contains f of this circle contains the point AB. If that is the case, then fxy, there's another condition, right? So f is defined on a disk that contains AB, right? And fxy, these two functions, a disk D and fyx, both are continuous, continuous on the disk, right? They're both continuous on the disk. If that is the case, then if these two hypotheses are true, then we have the following conclusion: fxy at AB equals fyx at AB. Right? So f has to be defined on a disk that contains AB, and both fxy and fyx have to be continuous on that disk. Right? If that is the case, then fxy equals fyx. So this the simple way of stating this is to say partial derivatives commute. Right? Partial derivatives commute. Right, so let's put this in in different notation. You have fxy equals fyx equals partial square f, or partial y partial x, right? And this is equal to partial square f over partial x partial y. So both are equal. All right, so I think that's enough for 14.1, right? Please have a look at the examples of. Please have a look at the following examples. I mean, if you still have trouble calculating partial derivatives, right, of higher order, please have a look at the following examples, right? The partial derivatives of higher order, right? And show that. And I also want you to look at example 9, right? That's that involves a partial differential equation. So partial differential equation is basically a differential equation with partial derivatives, right? And most differential equations you'll see in science and engineering are partial differential equations. So you have this partial differential equation called the wave equation, partial square u over partial t square equals a square partial square u over partial x square. This is what is known as a wave equation, and I want you to plug in sine of x minus at, ux equals sine of x minus at, to see that this satisfies the wave equation. Right, and of course there's another famous partial differential equation that occurs in many branches of science. It's called Laplace's equation, partial square u over partial x square plus partial square u over partial y square. You just plug in uxy equals e to the x sine y to see that this is a solution to Laplace's equation. Alright, so and of course this is the extension of Laplace's equation to 3 dimensions, right? Okay, cool. So now what we will do is we will look at tangent planes. Right. I think I'm going to give you this give you the Cobb-Douglas production function as an assignment question. Right. Okay, so let's look at tangent planes, right? How do we find the tangent plane to our surface, right? So if you recall, in single variable calculus, we were asked to find the tangent line, right? Find the line that is tangent to find the line that is tangent to a curve at a particular point. What we want to do is we want to find the plane that is tangent to a particular surface. We want to find a plane that is tangent to a particular surface. So the description of the problem is this. Problem. Find the plane tangent to the surface z equals f xy at x equals x naught, y equals y naught. Right? We want to find a plane that is tangent to the surface. Right. Now, one of the ways of finding the tangent plane is by determining a vector which is perpendicular to the plane, right? So now if we know a vector that is parallel to the plane, we could just dot it with the vector that is perpendicular to the plane and set that equal to 0, and we get the equation of a tangent plane. Now, let's say you have this surface. I'm not going to draw my axes, I'm just going to draw the surface. And then this is the point x naught, y naught, right? So remember we had two curves, right? C1 and C2 going over there, going through the tangent, going through the point in question, right? X naught, y naught. So, and each curve had a corresponding tangent line, right? So let's say so this is the tangent line to C1, and let's say this is the tangent line to C2, right? So let's call this so let's have T1 and T2, right? So T1 and T2. Okay, so now let's treat T1 and T2 as vectors, right? And T1 and T2 are going to span the tangent plane, right? T1 and T2 are going to span the tangent plane. Okay, so what do I mean by that? We treat T1 as a vector. T1 is given by this vector, right? T1 is given by this vector. Let's call it I plus f x naught, y naught, k, and let's say T2, because when you're moving along, why is this defined this way? Because when you're moving along T1, right, y is a constant, right? So j hat does not appear here, right? So when you move one unit along T1, you in the x direction, you move fx x naught y naught units in the z direction, right? And T2 is defined as j fy x naught y naught k. Now why is it defined this way? Because when you're moving along T2 in the x direction, I mean T2 is moving along the x direction, right? So sorry, T2 is moving along the y direction, so x does not change, right? So delta x is 0. So but if you move one unit in the y direction, then you move fy x naught y naught in the z direction, right? So T1 and T2, they are vectors on the plane. So a vector that is tangent to the plane, the vector that is perpendicular to the plane could be given by T1 cross T2 is perpendicular to the plane. Perpendicular to the plane, right? So let's find T1 cross T2, right? So T1 cross T2, let's set up our cross product determinant, ijk 1 0 fx 0 1 fy, and you end up with I fy I times fy, right? Sorry, I times negative fx minus j times fy plus k hat. right? So we got negative fx I hat negative fy j hat plus k hat. And remember that all of these derivatives are being evaluated at x naught, y naught, x naught, y naught, right? So this is perpendicular to the plane. Now let xyz be a point on the plane, right? It will be an arbitrary point on the plane, right? Then on the tangent plane, remember, tangent plane, then x minus x0 I hat plus y minus y0 j hat plus z minus z0 k hat is a vector on the tangent plane, and the dot product of this vector with the vector perpendicular tangent plane is going to give me 0 at x0, y0, z0, meaning this guy x0, y0, x minus x0 minus fy x0, y0, z minus z0 plus and then you have sorry, this is y minus y0. So that's x0, y minus y0, z minus z0 equals 0. So the equation of the equation of the tangent plane can be written as zxy equals z naught plus fx at x0, y0 as x minus x0 plus fy x0, y0 times y minus y0. So this is the equation of the tangent plane at x to the surface z. So this is what this is this the equation plane to z equals f of xy at x naught, y naught. Okay, so this is the equation of the tangent plane. Cool. Right, so let's look at an example. Let's look at a worked example of this. So let's say we want the tangent plane to the elliptic paraboloid z equals twice x squared plus y squared at the point 113. Well, first we need so our x naught. So our x naught is what? X naught is equal to 1, y naught is equal to 1, and z naught equals 3. I mean, you can find z naught just by plugging in x naught and y naught into f of xy. Right, so f sub x of xy equals 4x, and f sub y of xy is twice y. F sub x at 1, 1 equals 4, f sub y at 1, 1 is equal to 2. And the equation of the tangent plane is then z minus, remember this is z minus z naught, x for x minus x naught, y minus y naught, and this is of course fx, this is fy, and you get the equation of the tangent plane. Okay, so if you recall in single variable calculus, right, that you could that if you zoomed in to into a graph, right, if you have y equals f of x, right, some curve. Let's say you want to zoom in into this portion, the more you zoom in, the more this looks like a line, right? Zooming into a graph, into a curve, makes it look like a line. Look like a line, right? Now, what does zooming into a surface look like? What does zooming into a surface make it look like? All right, the more you zoom into this surface, for example, so you see what's going on here? So you have, so this is defined between -4 and 4. All right, so you see this is the graph between -4 and 4. So this is the elliptic paraboloid z equals x twice x squared plus y squared, and this is the tangent at 1, 1, 3. Here we're zoomed in. All right. Notice how the surface gets closer and closer to the tangent, and here we're zoomed in even more. Right, and now the surface, it almost looks like the tangent. Right, so the more you zoom in, the more it looks like the tangent. And that is why we're able to make a tangent approximation. Okay, so now if let's say we have the equation of the tangent, right? Z equals Z, of course, is going to be some linear function of x and y, z0 plus f of x at x0, y0, x0, sorry, x minus x0, plus f of y at x0, y0, y minus y0. Now we have this expression, this linear function of z, right? A linear function, z is a linear function of x and y. We want to find an approximation for z, we want to find an approximation for, the problem is we want to approximate f of xy near x0, y0, right? We want to approximate this near near x0, y0, and we're going to do this using the equation of the tangent. So this tangent equation, this is going to provide me with a linear approximation, right? So near x0, y0, we will call the approximation Lxy. This is equal to z0 plus fx x0, y0 plus times x minus x0 plus fy x0, y0 y minus y0, right? So this is a linear approximation near x0, y0, right? Linear approximation near x0, y0. Okay, so Lxy, L for linear. So we'll look at the example that's given in the textbook. Let's go back to the elliptic paraboloid example, and we found that this was given. We found that the tangent equation at 1, 1, 3 is given by z equals 4x plus 2y minus 3. So let's use that as our linear approximation, right? 4x plus 2y minus 3, which this is also called the linearization, right? The linearization of f at 1, 1. Okay, so let's look at the function. So we want to evaluate, let's say we want to evaluate f of 1.1 which is close to 1, and comma 0.95, which is also close to 1. Alright, so f of 1.1, 0.95. If I want to use a linear approximation, then I just plug in 1.1 and 0.95 here, and I get 3.3. But what is the exact value? What is the exact value? This is I mean, this guy. This is I mean, sorry. This thing. This is actually equal to L of 1.1, 0.95. Right. Well, what is the exact value? The exact value is f of 1.1, 0.95, which is equal to 2 times 1.1 square plus 0.95 square, which is 3.3225. And this is, and we have good agreement, 3.3, and I mean, it's correct to at least one decimal place. It's correct to exactly one decimal place. But if it's far away, right, such as, for example, the point 2.3, then L of 2.3 is 11, but F of 2.3 is 17. So that's a big difference. Right? So this is the linearization function. Okay, so we've looked at the tangent function. We looked at the linear we looked at finding how to find the tangent. We've looked at tangent plane approximation or linearization, and then what we have, we're going to have a notion of differentiability. Right, we're going to introduce a notion of differentiability in more than one variable. Right, so usually, when you talk about differentiability, right, what is the definition of differentiability for one variable? Right, f. This is a theorem, right? When x changes from a to a plus delta x, right? When x changes from a, actually I should write this down. Let's talk about differentiability. Differentiability. Okay, I will try to explain the theorem that I'm using here in the consultation, but please just accept it to be true for now, right? And the theorem that I will be using is this: is that delta y so if y equals fx, then the increment in y, delta y, at a is given by f of x plus delta f a plus delta x minus f of a, right? So if y, if f is differentiable at a, if f is differentiable at a, if f is differentiable at a, then it can be shown that this is for, of course, single variables, right? Single variables. It can be shown that delta y can be written as follows. It can be shown that delta y can be written as f prime of a delta x, right, plus some small number epsilon delta x, where epsilon goes to 0 as delta x goes to 0. Right, so this is the notion. So this is the this is what you get if this this is a result that you have for functions of single variables if they are differentiable. So if f is differentiable at a, then this increment in y can be written as f prime of a times delta x plus epsilon delta x, and this is shown in chapter 3 of Stewart's calculus. We'll go over this during consultation if you're confused. Now, in multivariable calculus, right, we'll define differentiability in the following fashion. Right, if z equals f of xy, right? If z equals f of xy, now this is in multivariable calculus. Multivariable calculus. So I am given z equals f of xy, right? Z equals f of xy. Now, how do we define the notion of differentiability in multivariable calculus? So if z equals f of xy, then f is differentiable at ab, f is differentiable at ab, alright, if delta z can be expressed in this form. And since we've been using x naught y naught, let's continue using x naught y naught. Right, x naught y naught. So ab is x naught y naught in the following form, meaning delta z, which is of course equal to the change in z as x goes to x plus delta x, and delta z, which is defined as f of x plus delta x, comma y plus delta y, y naught, right? If this can be expressed as we want to be able to express this as x naught y naught, not ab, times delta x plus fy x naught y naught delta y plus epsilon 1 delta x plus epsilon 2 delta y, right? And as you would have guessed it, epsilon 1 epsilon 2 go to 0 as delta x, and delta y, they go to 0. And these guys, epsilon 1 and epsilon 2, are functions of delta x and delta y. Notice the similarity between between this definition, this theorem, right, for single variable calculus, and this definition for multivariable calculus. So it's derivative times delta x plus epsilon 1 delta x plus another derivative times delta y plus epsilon 2 delta y. And in single variable calculus, you had a derivative times delta x plus epsilon delta x. And in both cases, as the delta x and delta y go to 0, the epsilons go to 0. Okay, now given this definition of differentiability, now this is not a working definition. this is not a working definition of differentiability, in the sense that it is hard to use this definition to check for differentiability. Right? So what we want is a convenient definition of differentiability, which we will prove. I mean, I'm not going to give you the proof right now because it's going to distract from the flow of the lecture. But the theorem is, right, if the partial derivatives of f, if the partial derivatives fx and fy. So far we've looked at the definition of differentiability in 2 and 3 dimensions. Now let's look at the theorem that tells us how we're going to use that definition. Theorem. I mean, this theorem is derived from the definition. If the partial derivatives fx, fy, these two partial derivatives, if they exist near AB, again, I'm using the language from the book, so instead of AB, let's use x naught, y naught, and are continuous at x naught, y naught, at x naught, y naught, then we can conclude that f is differentiable at x naught, y naught. So our definition basically told us that if the tangent plane is a good approximation for our for a function, then of course we call it differentiable, right? So, and this tells you that if the partial derivatives they exist near x naught, y naught, right, and are continuous at x naught, y naught, then f is differentiable at x naught, y naught. And the question is, I mean, what do we mean by exist near x naught, y naught and continuous at x naught, y naught? So let's try to illustrate that with an example. Sorry, what I was asking is what do we mean by, I mean, obviously you know what it means to say it's continuous at x naught, y naught. So what does it mean to exist near x naught, y naught, right? So let's look at an example of this. So let's say we're dealing with this function fxy equals x e to the xy, right? And this is differentiable at 1, 0. How do we show this? Well, we find fxy and fy xy. Now fx is exy plus xy e to the xy, and fy is x squared e to the xy. This is differentiable. These functions are differentiable. These functions exist everywhere, right? These functions, they exist everywhere on R2, right? And they're continuous everywhere, right? These guys, they're continuous everywhere, not just near. Our theorem just requires us to find derivatives that are continuous near x naught, y naught. But these functions are the fx, fy. These derivatives are differentiable everywhere, and are continuous at AB. Of course, they're since they're continuous functions. So these guys are continuous as well. They're continuous everywhere. So we want the partial derivatives to exist near AB, and we want them to be continuous at AB, right? Or x naught, y naught. So they're both and this function satisfies both conditions, right? Since it's continuous everywhere. Since they're continuous everywhere, sorry. And of course, fx and fy are continuous functions, and hence f is differentiable at x0, y0, and the linearization is of course the equation of the tangent plane on one side, and the linearization gives you the approximation at f of 1, f1.1 and negative 0.1 to be equal to 1, and of course from the function value you get 0.98542, which is pretty close. Okay, so that's that. Actually, and then we move on to the final bit of this chapter. Is we use which is differentials, right? Remember, in single variable calculus, you used to treat the derivative as a numerator and a denominator. For example, you had if you had dy over a dx equals fx, f prime x. I mean, you could think of dy as the numerator in a fraction and dx as the denominator in a fraction, right? Numerator, and this is a denominator. And you could write things like dy equals f prime x dx, and you could approximate the change in y as f prime, let's say at any point x0, f prime x0 times dx. That's the times the change in x. Right? You could do things like this, right? Now, can we do the same? And why did that work? Because you were using a tangent approximation. Again, we're dealing with tangent approximations, right? So this is so dy is actually how much the tangent vector changes, right? Dy tells you how much the tangent line changes, and delta y is the actual change in fx, right? Now dy is of course known as a differential. Now my question is, how much would z change, right, if x changed by delta dx and y changed by dy, right? So the total differential is defined as total. Okay, so we start off with the function z of f of x, y. The total differential is defined as delta dz equals df over dx times dx plus df over dy dy. Right? This is the definition of the total differential. Now we can use this definition of total differential to approximate changes in a function, right? To approximate changes in a function. Just as we use the total differential with in single variable calculus to approximate changes in functions of single variables, we can use the total differential to approximate changes in functions with multiple variables, right? So let's say you have a surface given in blue, right? And you want to find what happens, how you want to find delta z as z goes from you want to find the change in z as x and y go from ab to a plus delta x and b plus delta y, right? So delta z is of course the final value here minus the initial value here. But I want to find now let's say you're not able to find the exact value, so you want to find an approximate value. So what do? you use the linearization, use the tangent plane, right? So if the change changes in delta x and delta y, if the changes delta x and delta y are very small, the change in z can be approximated by the change in the tangent in the tangent plane. So dz, right, is basically the change in, is how the tangent plane changes when you go from AB to A plus delta x, comma B plus delta y, right? So that's that. So for example, so let's look at this example, and with that we will wrap up this lecture. And examples 5 and 6, I would like you to look them up on your own. Okay, so let's look at example 4. Right, so you have a surface given by z equals f of xy, x squared plus 3y squared minus y squared. Right? How would you find dx? It's a dz. Right, so the differential dz, remember, equals df over dx plus df over dy, dy, right? So, and then you just plug those in. Now, if x changes from 2 to 2.05 and y changes from 3 to 2.96, compare the values of delta z and dz. Okay, so delta z is of course the exact value, right? Delta z is basically your f of 2.05 comma 2.96 minus f of 2 comma 3. This is the exact value of change, right? Exact value, exact change. And dz is of course the change in the tangent plane, right? So dz gives you given that actually change in the tangent plane, given that dx is 0.0, x changes from 2.2 to 2.05 and y changes from 3 to 2.96. So delta x is obviously 0.05 and delta y is negative 0.04, and that gives you an increment for dz. And now notice that dz is 0.65 and delta z is 0.6449. So delta z is approximately equal to dz, but since dz is a linear function, it's easier to compute, it's easier to calculate, right? So with that we end lecture, I don't know, this is lecture 4, I think. We are done with section 14.4 of Stewart's calculus, and we're halfway through the chapter on partial derivatives, and from next class hopefully we'll continue with things like the chain rule and with partial derivatives and things such as the maximization and minimization problems. Okay, so I'll see you in class on hopefully on Monday next. Right.